In this video, we solve problem number 10 from written homework number 7 in the spring 2021 semester of elementary differential equations at Tulsa Community College. You're asked to use the Laplace transformation to solve the IVP, and what we have is a system of three equations with three unknowns. It's written in vector form, so let's think of it this way. If we've got a 3 by 3 matrix here, we want to let x of t be a vector with components x of t, y of t, and z of t. Then x prime would be the vector with components x prime, y prime, z prime. It's just like in calculus 3, you take the derivative component by component. We just use slightly different notation here. In linear algebra and most other courses, rather than writing r of t sort of in a row, we write it as a column vector like this. It's got 3 rows and we have a single column. Okay, so given that, then this equation, let's say the differential equation, can be written this way. It's x prime, y prime, z prime, that's our x prime on our capital X prime on the left-hand side, equals this matrix times the vector with components x of t, y of t, and z of t. Often we suppress this dependence on t. We just don't write it, but we remember x, y, and z all depend on t. So this is the same as this. And if you want to, you can write this as a system of 3 equations and 3 unknowns, and I would recommend that. So if x prime equals the result that we get when we multiply, or we take the dot product of this row with this column. So the dot product of this row with this column is -5 times x plus 6 times y minus 3 times z. And to get the second row first column entry, we take the second row and the first column and we dot them. So we'll have -1 times x plus 2 times y minus z. It's just a dot product. And to get the third row first column entry, we take the third row of this matrix and we dot it with the first column of that matrix. So I'll have 4 times x plus or minus 4 times y plus 2 times z equals that z prime. So that's the differential equation. And x of 0 equaling this vector just means that this vector, x of 0, y of 0, z of 0, is equal to 0, 3, and 5. Now, 2 vectors are equal if and only if their entries are equal. So this is telling us that x of 0 equals 0, and y of 0 equals 3, and z of 0 equals 5. So that's our initial condition, and this is what we have here. Okay, so we want to use the Laplace transformation to solve this. We want to find x of t, y of t, and z of t. So we'll do the same thing that we always do. We introduce our notation. Let the Laplace transform of x be capital X of s, and the Laplace transform of y of t be capital Y of s, and the Laplace transform of little z of t would be capital Z of s. Okay, so we start there, and then we'll take the Laplace transform of each of the differential equations. So I'll call those d sub I for I equals 1, 2, and 3. Okay, so if this is my first one, this is my second one, and this is my third, we just want to take the Laplace transform of both sides one at a time and use our initial conditions to simplify from there. Actually, let's do the Laplace transform of the first equation. Well, first we'll have the Laplace transform of x prime on this side equals -5 times the Laplace transform of x plus 6 times the Laplace transform of y minus 3 times the Laplace transform of z. Do you see that that's just going to be x of s, y of s, and z of s because of this definition? That's going to be the same for each of these equations. So the left-hand side is going to be or excuse me, the right-hand side is going to be really easy, but the left-hand side is just a little bit more involved. It's the Laplace transform of a derivative, so it has a couple of terms. So let's write that out now. The Laplace transform of the first derivative gives us an s to the first times x of s minus x of little x at 0. And this will equal all of this. And from our initial condition, x of 0 is 0. So we have this now. So if I want to write this in such a way that I can use Cramer's rule to solve the system of equations later, I want the x's, y's, and z's on one side, and any functions of just s only, or any functions that don't involve the x, y, and z, I want those on the other side. So we'll add 5 times x of s to both sides, and then we'll group the x of s terms. So we'll have s plus 5 times x of s minus 6y of s plus 3z of s equals 0. And that's our first equation. We want 3 equations and 3 unknowns. To get the next equation, we take the Laplace transform of the second differential equation. So that's the Laplace transform of y prime equals a -1 times the Laplace transform of x, which is x of s, plus 2 times the Laplace transform of y, it's our big Y of s, minus the Laplace transform of z. So you have z of s there. And this, using the same rule that we used here, is s to the first times y of s minus little y at 0. Okay, now we have y of 0. Y of 0 was 3, that was given to us from our initial condition. Now when I write this in a slightly different way, I want a function of s times x. So I'll add the x of s to both sides, plus a function of s times y. So I will subtract the 2 times y of s from both sides and factor out the y of s. So I've got s of them, and I'm subtracting 2 of them, so I have s minus 2 times that. And then I'll add the z of s to both sides. And this 3 doesn't have an x, a y, or a z in it, so I will add 3 to both sides. And that's giving me my second equation. Got 2 equations and 2 unknowns, or 2 equations with 3 unknowns now. I just need 3 equations and 3 unknowns, and I can find the last equation by taking the Laplace transform of the second, or the third differential equation. So I have the Laplace transform of z prime is equal to the Laplace transform of all the expressions on the right-hand side. So that'll be 4 times x of s minus 4 times y of s plus 2 times z of s. And the Laplace transform of z prime is s times the Laplace transform of z, which is z of s minus little z at 0. And little z at 0 was 5. It was given in the initial condition, so this is a 5. So if we subtract 4 times x of s from both sides, we have that. Then we'll add this to both sides to get our y term next. And then we want our z term. So I have s of those here, and I've got 2 of them over here. So when I group them, I'll subtract 2 times that from both sides and then factor out the z. Add 5 to both sides, and we'll end up over there. And then, so that's our third equation. So we've got 3 equations and 3 unknowns. S plus 5 times this. And then we have x times this. And then we have -4 times x here, plus this. Okay, so we've got 3 equations and 3 unknowns. Now you can write this in matrix form this way. List the coefficients of x, y, and z here. So I'm just focusing on what's multiplying my x, what's multiplying my y, what's multiplying my z. There's an implied 1, an s minus 2, and a 1, a -4, a 4, and an s minus 2. That's being multiplied by x of s, y of s, and z of s. And that equals this right-hand side of 0, 3, and 5. Well, we can solve for x of s, y of s, and z of s by using the Cramer's rule, So according to Cramer's rule, the denominator is just the determinant of this matrix here. And that'll take a little bit of work. But fortunately, we only have to do it once because we're going to use the same denominator for all of these. And for the matrix in the numerator, the second and third column stay exactly the same, but you replace the first column, because we're talking about the first variable, with 0, 3, and 5. So we need to evaluate this, and we're going to use that 3 times. And then this one we'll have to do separately. Okay, so let's do this one. Let's evaluate that determinant from the denominator. And you can expand along any row or column you want. Since there aren't any rows or columns of zeros, I'm just going to expand along the top one. Remember that sign convention, it's plus minus plus. So we'll have plus s plus 5 times the determinant that comes from crossing out the row and column containing that s plus 5. So this is s minus 2, a 1, a 4, and an s minus 2. And then we're subtracting a -6. So that's going to be an adding 6. And then we cross out the row and column containing that -6. So we'll have a 1 and a 1 in the top row, and a -4 and an s minus 2 in the second row. And then we add 3 times the 2 by 2 determinant that comes from right here, crossing out that row and that column. So we'll have a 1, an s minus 2, a -4, and a 4. So this is s plus 5 times s minus 2 squared. You could write that out as s squared minus 4s plus 4. And then you're subtracting 4. Here we have 6 times s minus 2 minus a -4, so we're adding 4. And here we've got 3 times 4 minus -4 times this. So we're adding 4 times the quantity s plus or s minus 2 there. So these guys reduce. And this actually gives me an s plus 5 times, if I factor out an s times s minus 4. And here I've got a 6 times s plus 2. And over here I have a 3 times 4s. Minus 8 plus 4 is going to be minus 4. Yeah, I was hoping for a common factor, but we didn't have any common factors. So we're going to have to distribute all of this. So I think I would prefer to write that this way as it was originally. And now we'll distribute. First times first is s cubed, outer times outer is -4s squared, inner times inner is 5s squared, and last times last is -20s. Plus the 6s plus 12, just bring that down, plus 12s minus 12, and reduce anywhere you can. The 12 and the -12 reduce, okay. My s cubed term, there's only one of them, so I could write that down. I've got a -4s squared plus 5s squared, so that's going to be a positive 1s squared. And the 6s and 12s is 18s. -20s plus 18s is -2s. So that is our denominator, and we might want to factor out an s. And this factors in this way. It's going to be s plus a constant times s plus a different constant. I need two numbers that multiply to give me -2 that add to 1. If there's a +2 there and a -1 there, it'll work. So I'll have 2s minus 1s is a positive 1s, and 2 times -1 is -2. So that's my denominator. So s times s plus 2 times s minus 1. And my numerator is this matrix. I have a 0, 5, a 3, and a 5, and the second column stays the same, and the third column stays the same. I will expand along this column, plus, minus, plus. The sign convention always starts at the top at plus, then minus, then plus, and then you pick up where you left off, minus, plus, minus, plus, minus, plus. But if n is odd and it's a square matrix like this, it's going to alternate down the rows, or across the rows and down the columns. So I'll have plus, minus, plus here. So this would be 0 times the determinant that would come from crossing out the row and column containing 0, but multiplying anything by 0 doesn't do anything. So we'll leave that off because we know we're going to get 0 there. And then we'll subtract 3, and we'll multiply by the determinant that comes from crossing out the row and the column containing that. So we'll have -6 and 3 in the top row, and a 4 and an s minus 2 in the bottom row. And then I have plus 5. Cross out this row and this column. We've got -6 and 3 and s minus 2 and 1. Alrighty. So now we'll just distribute this -6 times that quantity, -6 times s, -6s, -6 times -2 is positive 12. And then we're subtracting 12 there. Then we're adding 5 times this, which is -6. We subtract 3 times this. So it's like multiplying this by -3. So we'll have a -3s, -3 times -2 is positive 6. Those guys reduce. Those guys reduce. And we end up with 18s minus 15s is 3s. So we have 3s right there. And that's nice because the s's reduce, and then this is just a constant over s minus a times s minus b, and we have a rule for that in our table. You could use partial fraction decomposition for this in order to get x of t, but it's not necessary because there's a rule for this in our table. So you've got a 1 over s minus a times s minus b right here. This is entry number 28. In our case, our a is -2 and our b is 1. Let me write this down. The inverse transform of 1 over s minus a times s minus b is e to the ab minus e to the bt divided by a minus b. So when I am going from here to my x of t, I'm going to apply that rule, and I'll factor out the 3 so that I've got a 1 in the numerator. That's the plan. That's where we're going with this. X of t is 3 times the inverse transform of 1 over s plus 2 times s minus 1. So we have 3 times e to the at minus e to the bt. A is -1, b is 1. So I have a minus b in the denominator, and e to the at minus e to the bt in the numerator. So I end up with a 3 and a -3 in that denominator. So that's going to reduce to a 3 divided by -3, which is -1, times e to the -t minus e to the t. If you distribute that negative, you'll get e to the t minus e to the -t as your x of t. Okay. So that's what we have right there as x of t. Now, we also want to find y of t. The denominator is going to be the same, but y of t's numerator is a little different. Or y of s's numerator. So according to Cramer's rule, we'll have this. The coefficients matrix, its determinant goes in the denominator here. And we've already done that work. It turned out to be S times S plus 2 times S minus 1. And in the numerator, you leave the first and third columns alone because you're talking about the second variable. And you replace that middle column with the right-hand side over here, which is 0, 3, and 5. Now you can expand along any row or column you want. I usually like to expand along a row or column that has a 0 in it. And so we've got options. We can expand along this one, or we can expand along this one. I think I'll expand along this one just because that's more of what we're accustomed to. At least with the sign convention, it's going to be plus minus plus as opposed to minus plus minus, which might throw some people. So let's evaluate that now. Expanding along the top row, plus minus plus. It's going to give us a positive S plus 5 times the 2 by 2 that comes from crossing out this row in this column. So I'll have a 3, a 1, a 5, and an S minus 2. Then we're subtracting 0 times something. It doesn't matter what that is because it's just going to be 0 when we multiply it by 0. And then we have plus 3 times the determinant that comes from crossing out the row in the column containing the 3. So we have a 1, a 3, and negative 4, and a 5 there. So this is going to give me S plus 5 times this, 3 times this quantity. If I distribute the 3, I'll have 3S minus 6. And then I'll subtract 5 there. And then I have the 0, and then I have 3 times over here 5 minus a negative 12. So that's going to be plus 12. So I have S plus 5 times 3S minus 11, and 5 plus 12 is 17, and 17 times 3 is going to be, what, 30 plus 21, 51. Okay, so now let's work this part out. First times first is 3s squared. Outer times outer is negative 11s. Inner times inner is positive 15s. And last times last is negative 55. And we're adding 51. So this is going to be a 4s if we combine like terms. And the negative 55 and the 51 will give us a negative 4 there. Now, you can just, you can factor this a number of ways. You could use factoring by grouping if you don't want to guess, or you can just guess. And the guessing method might work just fine. We know that first times first has to give us this 3s squared. So we know we have to have a 3s here and an s here. And we also know that outer times outer and inner times inner has to add to a 4s. And last times last has to multiply to give us a negative 4. So I'm thinking with a 3 and an s, a 3s and an s, in order to get a 4s in the middle, I can't use 2 and negative 2 for this 4. I'm going to have to use a 4 and a 1. If I put a 4 here and a 1 here, that will work because I'll have a 4s and a 3s. Will it? No, it's not going to give me that 4s that I want in the middle, is it? Let's think about it. I'd have a 3s. If I wanted that to be a positive number in the middle, I'd have a plus 4 and a minus 1. So I'd have negative 3s plus 4s would be a positive 1s, not a 4s. So that won't work. Let's see, what about the other way? What if I put a minus there and a plus there? So then I'd have 12s minus s, and that's going to give me an 11s. Nope, that won't work. Okay. How about, I guess we are going to have to use 2 and negative 2. Well, and that makes sense actually, because if I have a 2 out here, that'll be a 6, and a 2 in here, that'll be a 2s. So I'll have 6s and a 2s, and if they have the right signs, I could get a positive 4s in the middle. If I want a positive 4s, that means that this times this, the 6s has to be positive and the 2s has to be negative. So outer times outer is 6s, inner times inner is negative 2s, 6s minus 2s is the 4s, and last times last gives us the negative 4. Awesome. So that is the numerator for our y of s over here. So we have 3s minus 2 times s plus 2. And these guys reduce, and now we just have 3s minus 2 over s times s minus 1. Now you have some options with that. You can split it into a number of pieces. We could say that y of s is equal to 3s over s times s minus 1 minus 2 over s times s minus 1. And then the s's would reduce, and we'd get 3 over s minus 1 minus 2 times the quantity 1 over s times s minus 1. This is another example. Oh, I was going to say it's another example of that 1 over s minus a and s minus b, but I don't think that we can use that rule when a is 0. I don't know that that works. Let's see if we can't find something like that in our table. If not, maybe s equals, or a equals 0 does work. As I look at these second columns, I don't see any that just have an s times s minus a. But this pattern that we used before for a 1 over s minus a times s minus b would seem to work. But if a is 0, this would just be a 1 minus e to the b over 0 minus b. I don't know that that's going to work. I guess we're going to have to use partial fractions for that piece. And that's okay, because partial fractions are relatively easy for us at this point. So let's use partial fractions to rewrite the negative 2 over s minus, or s times s minus 1. So I have a over s plus b over s minus 1, since these are both linear factors and neither of them are repeated. If I multiply both sides by the LCD being this denominator will cancel and I'll just have the numerator. And if I take this and multiply by this, the s's will cancel and I'll have a times s minus 1. If I take this expression and multiply by this, the s minus 1's will cancel and I'll have a b times s. If s equals 1, we have negative 2 equals b. And if s equals 0, we'll have negative 2 equals negative 1 times a, so a equals positive 2. So that means this fraction, or this sum of two fractions, is actually 2 over s minus 2 over s minus 1. So let's substitute that in over here. That 3 over s minus 1 plus a, which is 2 over s, plus b, which is negative 2 over s minus 1. And I've got 3 of those there, and I'm subtracting 2 of them, so that means I'll only have 1 of them. So that is our y of s. Y of t is the inverse Laplace transform of y of s. Inverse transform of this piece, that's 1 over s minus a, where a equals 1. It's going to be an e to the a t, so it'll be e to the 1t, plus 2 times the inverse transform of 1 over s, which is just 1. So y of t is equal to this. All right, so we've got our y, we've got our x. Now we just need to find our z. And finding z is very similar. We just need the determinant in the numerator for Cramer's rule. The denominator is going to be exactly the same. So remember that denominator was s plus 5, negative, or 1 and negative 4 in that first column. We had a negative 6, a 2 minus, or s minus 2, and a 4 in the second column, and a 3, a 1, and an s minus 2 in the third column. Now the first two columns are going to stay exactly the same. But for our third variable, we replace the third column with 0, 3, and 5. That's the vector from the right-hand side of that equation that we had written in matrix form. There we go. Now this denominator we've already worked out. It's s times s plus 2 times s minus 1. And the numerator requires a little bit of work. So let's expand along this column now. We have plus, minus, plus, minus, plus, minus, plus, minus, plus. So we ignore all of these signs over here and we just keep the plus, minus, plus. Okay. So expanding that now. Along this column, we'll have 0 times the 2 by 2 determinant that comes from crossing out the row and the column containing that 0. 0 times anything is 0, so we're not going to do the work. Well, we are doing the work, but we're simplifying the work by choosing wisely. And then the next part is -3 times what we get when we cross out the row and column containing the -3. We've got an s plus 5 and a -6 in the top row and a -4 and a 4 in the second row. And then the last one is a +5 times what we get when we cross out the row and the column containing the 5. So I have an s plus 5, a -6, a 1, and an s minus 2 here. So I have -3 times this determinant. If I distribute that 4, I get a 4s plus 20. And then I'm subtracting 24 from that. And over here, I have 5 times s plus 5 times s minus 2. If we distribute, we'll have first times first is s squared. Outer times outer is -2s. Inner times inner is 5s. 5s minus 2s is 3s. Last times last is -10. And then we're subtracting -6. That means we're adding 6. So this ends up being -3 times 4s minus 4. If you want, you can factor off the 4. You'd be left with a -12 out here because the 4 times the -3 gives us that -12 times an s minus 1. And then over here, we'll have s squared plus 3s, and -10 plus 6 is -4. And I don't know that that factors nicely, does it? There are two numbers that multiply to give us -4 that add to 3. I think so. That's a 4 and that's a minus. +4 and that's a minus. 4 times -1 is the -4, and 4 plus a -1 is the 3. So that'll work. Now you could have just distributed and collected like terms and then factored from there, but I did that instead because now they have an s minus 1 in common and I can sort of factor by grouping. I look at this group and I see that they have an s minus 1 in common, so I write that down. And then I say to myself, okay, s minus 1 times what? Give me the first group, -12. And s minus 1 times what? Give me the second group. Well, I'm missing the 5 and the s plus 4. So let's distribute that 5. And 20 minus 12 is 8. Okay, so that is our numerator. For our z's. And the z minus 1's reduce, and we end up with this 5s plus 8 over this. I think I'll just go straight to the partial fractions. It's going to be a over s plus b over s plus 2. We just need to find a and b so that this fraction equals the sum of these two fractions. This will be relatively simple because our factors are linear non-repeated factors. So we get a constant in the numerator for each factor, and we add those together to get the partial fraction decomposition of the original guy. So once you write down the partial fraction decomposition, you've got this. Then you multiply by the LCD, which is always the original denominator, and those will reduce. The s's will reduce, the s plus 2's will reduce. And then we'll have 5s plus 8 equals a times the quantity s plus 2 plus b times s. Now if s is equal to 0, the left-hand side is just an 8, and this b times s is going to be 0, so we'll have 2 times a over here plus 0. So a is 8 divided by 2, which is 4. Now if s is equal to -2, this is -2 times 5 is -10. -10 plus 8 is -2. Oops. And this will be a times 0 plus b times -2. And if we divide both sides by -2, we get a 1. So that means our z of s is 4, which is s, or is a over s, which is 4 over s, plus b, which is 1 over s plus 2. So z of t is the inverse Laplace transform of that, which just gives me a 4. And this is 1 over s minus a, where a equals -2. So we'll have e to the at, where a equals -2. So that's my z of t. So we've got our x, our y, and our z. And that was our y of t. That was our x of t, or z of t. Y of t was 2 plus e to the t. And I don't remember what x of t was. Feels like it's been a while since we started this, huh? X of t, long time ago, we found out that that was e to the t minus e to the -t. Now, the original equation, let's see, where did it go? It looked like this. So the expectation is that our answer will be in the form of a vector x of t. It'll be in the form of x of t with these components, x of t, y of t, and z of t. So the x of t, y of t, and z of t that we just found are the x, y, and z components of some vector valued function. We could think of it as mapping out a trajectory in space if we wanted to. And these are the component functions. So x of t, capital X of t, is the vector with these components. Now, if you want, you can differentiate and then substitute x of t into the right-hand side of this equation and multiply this by x of t and simplify, and you should get the same thing as you have for x prime. And if we evaluate these functions at t equals 0, we should get 0, 3, and 5. Here's hoping that actually works. So let's check. If t equals 0, I have e to the 0 minus e to the 0. So that's 1 minus 1, which is 0. Good. I was supposed to get 0 there. And if t equals 0, I've got 3 plus e to the 0, or 2 plus e to the 0. E to the 0 is 1. 2 plus 1 is 3. Good. I was supposed to get a 3. And this last one is supposed to be a 5. And it is a 5. If I substitute t equals 0 here, I've got 4 plus e to the 0, or 4 plus 1, which is 5. So I know that my initial condition is satisfied. But if I want to show that this is satisfied, I need to substitute this vector in right here, multiply. You know, you're going to do the same thing that we did down here, where you take the top row and this first row and the first column, and you take a dot product, and that's going to give you your x prime. Take the second row and the first column, it's going to give you your second component of x prime, and your third row and that column to get the third component of x prime. If you do that, provided that the solution is correct, you should be able to see that the left-hand side and the right-hand side are equal. So this is problem number 10 from written homework number 7 during the spring 2021 semester. Let me know if you guys have any questions about this. I'd be happy to help you.